Hi everybody, my name is Maksim Vazhenin and I am a software senior principal engineer at Dell Technologies. In this session I will talk about InfluxDB for storage system monitoring.
My agenda today will include following topics. Our journey to InfluxDB monitoring stack for ECS storage system monitoring, how we added high availability for open source version of InfluxDB, how we improved query compute layer by separating it out from InfluxDB and making it horizontally scalable, how we managed to deploy InfluxDB stack on relatively low memory resources, and finally, how we managed to switch monitoring stack in ECS storage in multiple stages. In the end, I will cover what benefits all this gave us and variety of dashboards we were able to build. Let's start on our journey to InfluxDB stack. To provide you more context for understanding all the challenges which we faced during our journey, I will tell you a few words about our product. ECS is the leading object storage platform from Dell EMC, boasts unmatched scalability, performance, resilience, and economics. Deployable as a physical appliance or in a software-defined model, ECS delivers rich S3 compatibility on a globally distributed architecture, empowering organizations to support enterprise workloads such as cloud-native, archive, Internet of Things, artificial intelligence, and big data analytics applications at scale. ECS is managed by customers, so we sell to customers real physical racks with software and we do not manage it. ECS is deployed on commodity hardware with a bunch of disks. ECS is horizontally scalable and has homogeneous nodes, so every node has the same services running on it. We do not have control plane nodes dedicated for management and monitoring. ECS is deployed on Linux operating system inside Docker containers. Main data path services run inside main container. Monitoring services run in separate Docker containers. Every container has its dedicated memory limits. Main Docker container for data path services, of course, has memory limits set to maximum available on the nodes after you dedicate a small part of memory for few orchestration and monitoring containers. ECS is an on-premise product which is managed by customers. It must have internal monitoring, which runs inside on the product. ECS internal monitoring is used to monitor the following aspects of the system. Capacity. There are a lot of capacity-related metrics in distributed storage, which require complex compute to prepare customer-usable statistics. Internal monitoring is also used for performance monitoring to provide P50 and P99 percentiles per node and per cluster. Monitor internal health from different services, and system monitoring for hardware resources utilization and health. When my team was moved to drive ECS internal monitoring, there was already an internal monitoring framework inside. It did a great job as a starting point, but had a few downsides. First, it required multiple teams' involvement to add some new dashboard in UI. A single team which owned the service, which was providing metrics for the dashboard, had no knowledge how to make changes on different software layers to add new dashboard. Our framework did not have flexible query language, and because of that, all the queries were written as a code inside the service which prepared data for UI or API. Framework also did not have a concept of continuous queries, which caused issues on large time range queries when complex compute had to be run for a huge amount of points to build historical view. Our team's goal was to find a solution to overcome the mentioned downsides and come up with a monitoring framework which would uncover the possibility to have autonomous service teams capable of adding new dashboards, a way to easily build new dashboards, a way to easily create new alerts, and new monitoring stack should provide detailed system resource monitoring. Main challenges for new monitoring solution were high-scale deployment of homogeneous nodes. Large customers have clusters of 300 nodes. and the fact that on a single node there is no room for linear vertical scale depending on the size of the cluster. Only a small amount of memory may be reserved for monitoring components on a single node. Almost all resources are consumed by data path services, so there is usually no free resources on a node. So monitoring framework should consume as low resources as possible. We had a limit of 3 GB of memory per node, which we could allow for monitoring services to use. It is okay to use 3 GB on each node, but no more than 3 GB on each node. As we already had some experience at monitoring TCS on test longevity environments, we did research to find open source monitoring solution which would suit our needs. The list of final candidates, there were 3 alternative solutions: Elasticsearch, Prometheus, and InfluxDB. We started our investigations from Elasticsearch, as lots of companies are using it due to its flexible analytics capabilities and practically unlimited ways to prepare high-quality, multidimensional views on different sorts of data points. But when we filled Elasticsearch with all the metrics from a single ECS cluster, we soon identified that all the flexibility comes with cost. And the cost was too high resource consumption, and there was no way we could run Elasticsearch cluster with 3 GB limits per node. Next solution which we considered was Prometheus. We already used it for test environments monitoring and knew that it shows great performance while consuming very low amount of disk space and has easy to use query language. Also, we were aware of the limitations with high cardinality data, which are problematic for lots of time series databases and usually require more resources, which we would not be able to provide. But plan with high cardinality data was to control and avoid. But Prometheus also had other issues which we identified during our investigation. Prometheus did not support backfilling at all at that time. And this was an important feature for us as we needed a way to fill the instance with missed points after downtime of one of the Prometheus instances. Another big issue for us was that Prometheus is not working reliably when receiving rare data points, and it is bad at counting exact values. When Prometheus has data points with rare interval, say we have polling interval defined to be 2 minutes, and want to calculate increase of a value for last 4 minutes. Prometheus will extrapolate the 2 data points to calculate increase for 4 minutes. Result will be inaccurate. The less points you have in the interval, the more inaccurate will be the result of aggregation functions, which will imagine the values which might be there at the ends of the intervals. It may be okay for some of the system metrics like CPU, but it is unacceptable for exact compute of capacity-related metrics in a storage system. So we decided that Prometheus also does not suit all our needs. Another alternative which we considered was InfluxDB stack. It had similar problems with high resources usage on high cardinality, but we planned to control cardinality of our metrics. First attempts to use InfluxQL showed that original language from InfluxDB lacks some very important features, like ability to perform cross-measurement computation. This was a blocker for us to use InfluxDB, as we had to run queries which would aggregate metrics from different measurements to produce final results. As in distributed storage, there are cases when metrics from multiple services needs to be combined to calculate final value. But at that time, InfluxDB announced new query language called Flux, and we validated that it is flexible enough to provide computation of any complexity which we would need. Also, InfluxDB showed great performance, consuming low memory and CPU resources per series and providing low disk utilization, which were comparable for Prometheus. We were able to successfully use Flux language for exact computation, even for rare metrics, and InfluxDB also supported backfilling. Elasticsearch and Prometheus did not meet our need, and we chose InfluxDB. As a result, for internal monitoring of our distributed storage, InfluxDB won the competition to be our new monitoring stack to which we will go forward. Next, I will cover our journey to InfluxDB high availability. So we decided to use InfluxDB as our main time series database, which will run on ECS cluster to provide internal monitoring. We created a Docker container for InfluxDB and changed our orchestration to deploy InfluxDB on one of the nodes in the cluster. We created a Docker container for Telegraph and deployed Telegraph on every node in the cluster to collect system-level stats, as well as acting as a proxy from services running on all the nodes and pushing statistics, and InfluxDB. So, services should not know where InfluxDB is located, they only need to push stats to localhost Telegraph. As UI for new monitoring framework, we selected Grafana and run Grafana in a Docker container on every node, as customer may access ECS UI on any node in the cluster. Inside Grafana, we added a script which will, on startup, provision all needed dashboards and create InfluxDB data source, taking InfluxDB endpoint from our orchestration layer. The POC was ready and we were able to build some basic dashboards for Grafana and see system health. But of course, we had the requirements from product management that ECS should work normally in case of two nodes failures. And in case it happens that a node on which InfluxDB is running goes down and is not accessible, all our monitoring data becomes inaccessible and we see nothing in our Grafana dashboards. This is bad. And remember that we do not have any sort of shared storage between the nodes, so you cannot just restart InfluxDB on a different node. InfluxDB stores data on local disk, so if node goes down, then data from that InfluxDB instance is not accessible from anywhere. What is the solution for this issue? Sure, run multiple instances of InfluxDB. To support two nodes down, we need to run 3 InfluxDB instances on different nodes. Telegraph send metrics to all InfluxDB instances. So we have 3 identical copies of InfluxDB. In Grafana, we have a template variable to select which InfluxDB to use on current dashboard. In case two nodes down with InfluxDB, we still have the third InfluxDB instance alive, and customer may see data points in Grafana dashboard after selecting a live InfluxDB data source. That's great. Seems like we now are satisfying PM's requirements to support two nodes down use case. But wait, what if after having two nodes down for some long time and after that revived, we have the third node down? In this case, a live InfluxDB instances will not have the data for the time range where they were down. So customers will not be able to see some ranges of data in this time until the third instance come up. It may be even worse if the third instance just burned out and we need to replace the failed node. This will cause losing the monitoring data which was stored only on the third instance. That's not good. To avoid this, we decided that we may recover the data on InfluxDB when the instance is starting up. To avoid problems with backfilling, we try to restore as much as possible on startup before we start InfluxDB on a port which is accessible for Telegraph. So we start InfluxDB in 2 phases. On first phase, we start on different port to avoid new writes from Telegraph and recover from other InfluxDB instances the time range for which InfluxDB was down. On second phase, we start on normal port and recover small amount of data points which were missed during first phase. If needed, we trigger recovery of the missing periods in background. This way, we ensure that we do not stress InfluxDB with huge amount of backfilling requests and write as many data on recovery in InfluxDB friendly, append-only fashion. We use standard InfluxDB backup restore API to perform recovery. For large time ranges, we split recovery to one-day parts to not cause out-of-memory issues in case node was down for several weeks, and we wouldn't try to recover all small data, all missing data in one big transaction. So now all is good, and we are able to support rolling failures or downtimes. And even we may handle rolling node replacement, which is an important scenario for tech refresh, when customer is replacing all hardware nodes with new ones, when all hardware comes to the end of life. As a result, using multiple instances of InfluxDB and backup restore API, we were able to build high availability setup for InfluxDB instances, which was able to handle two nodes down scenario and node replacement or tech refresh scenarios. Now I will move to the next step in our journey and tell you how we improved query compute layer by separating it out from InfluxDB and making it horizontally scalable. As you remember, when we added 3 instances of InfluxDB, we had to add a template variable in Grafana dashboards for customers to select a good instance of InfluxDB as a data source. That is not a great user experience to click on different InfluxDB instances, trying to guess which one is alive at this time and has fully recovered database for the needed time range. We started to think how we can improve this and found a solution. We decided that we need a separate compute layer which will consist of services running on every node and taking raw data from InfluxDB. We named the service after the new language of InfluxDB, FluxD. This architecture allowed us to have localhost FluxD service instances as a single data source for Grafana. Now we were able to even hide InfluxDB data source from customer and always use localhost FluxD as a data source. FluxD service should be smart enough to understand which InfluxDB instance is the best one to run each specific query. When query comes from Grafana or any other service to FluxD, it splits the query and sends raw request to InfluxDB. Raw request usually includes first 3 lines, from, filter, range. Some functions may also be sent down to InfluxDB, like last function, to speed up the request so that InfluxDB returns only last point instead of full range. FluxD selects the best InfluxDB instance, which has all recovered time range for a database used in the query. If query happens to have a time range which is partially present on all InfluxDB instances, for example, after downtime there were some issues to perform recovery right away and it will be recovered later, then FluxD is responsible to send the query to all InfluxDB instances and merge the results, deduplicating them during merge. Once FluxD gets the raw data from InfluxDB, it runs the rest of Flux compute for the query. This additionally offloads compute resource from InfluxDB instances, which do not scale horizontally, and so every reduce in resource consumption of InfluxDB is a big deal for us. As we had local FluxD data sources for Grafana and other services running on the node which need to run some monitoring queries, it caused issues with overloading one of the FluxD instances. And we built query layer to easily overcome such issues. Adding load balancing of queries allowed us to have minimal resource consumption on each individual FluxD instance, while still providing high throughput for queries. This ideally matched our need for distributed architecture for our monitoring framework, which scales horizontally. Another big advantage of having a separate compute layer is that the FluxD services are stateless. Losing some node with FluxD instance just removes one of the workers from the worker pool and does not really affect the cluster. As a result, by introducing compute layer, we improved user experience by having only a single data source in Grafana. We reduced resources needed for InfluxDB by offloading query to a separate compute layer. We ensured that all nodes received similar load of Flux queries, and this allowed us to have lower resource limits for each FluxD instance. And we built stable, horizontally scalable, stateless compute layer to serve FluxD queries. Next, I will cover details on how we ensure that InfluxDB and other components in its stack fit into our lower resource consumption limits. To avoid out-of-memory errors and Docker container failures, our monitoring stack should consume predictable resources and fit into 3 GB of memory per node. Main components of our monitoring stack are Telegraph, InfluxDB, FluxD, and Grafana. The most precious resource on our clusters is memory. We already saw how we offload compute from InfluxDB and lowered its memory needs. Let's see what other steps we had to perform to achieve predictable low resource consumption. Let's start from Telegraph. All services which run on a node send their metrics to local Telegraph instance, and we have defined periods when services may push metrics, so they do not do it in uncontrolled manner. But anything could happen, and on some error conditions, services may start push more metrics than expected, producing more load in Telegraph, which may cause more memory consumption by Telegraph. At some point, if services push too much metrics, Telegraph will hit its memory limit and will be killed by killer inside Docker container. That is not something we want to happen on error conditions. In case some services go crazy and start push more metrics than we expect, we would prefer to start dropping metrics than to be killed by ORM. This way we will drastically degrade our stack functionality instead of running into denial of service situation right away. To achieve this, we had to set specific memory buffers, limits, and batch size limits in Telegraph config. Having defined buffer limits, we also took into account the situation when some InfluxDB instances are down and the corresponding buffer will be always full. Telegraph keeps a separate memory buffer per each output, so if you need to handle some outputs to be down and ensure that Telegraph will not ORM, you need to provide extra room for full buffer for each output you define in Telegraph config. Now Telegraph has predictable memory for received metrics. We thought that we are done optimizing Telegraph and will never ever see any Telegraph restarts due to ORM. But on some day new escalation came from customer side. Telegraph has been periodically restarting due to out of memory. We were sure that it is not because of some metrics received from services on HTTP input, as we had all proper limits defined for memory buffers already. We started to dig into the issue more to understand the root cause. Of course, in Telegraph we used lots of different input plugins to gather different system metrics, and most of these plugins were embedded Go code. When investigating memory issues with Telegraph, we found that extra memory was consumed not by Telegraph itself, but by other binaries which were called from exec input plugin. We remembered that for some metrics which were not available in our service, we wrote a few scripts which were called from Telegraph exec input plugin to gather these metrics. It turned out that on some customer environments, on some conditions, these scripts may consume much more memory than we expected. And these scripts caused out-of-memory issues in Telegraph container. Later on, we found that not only custom scripts cause these issues, but some of well-known binaries used for exec input plugin also may consume much more memory than you would expect. So, what is the solution? Never use exec input plugin, especially if you run Telegraph inside Docker container and have low memory limits set for it. Always force service teams to add needed stats in their reporting instead of trying to collect them using custom scripts inside Telegraph. So we removed all the input exec plugins from our Telegraph, and now guess what? Telegraph never dies due to OM. We finally got it stable for our use case, and full Telegraph container uses memory limit of 150 megabytes. That's great. It is 100 megabytes more than we originally expected Telegraph to consume, but still very, very good. We are done optimizing Telegraph, and now it's time to look at InfluxDB. There are several factors which dictate how much memory will InfluxDB consume. Number of metrics you push to InfluxDB, metrics cardinality, retention period of your databases, compute resources for complex queries. We already saw how we offloaded complex compute out of InfluxDB. Let's see what we can do with other factors. When we first set up InfluxDB to get all the metrics available in the cluster, we were disappointed in the amount of memory it took for InfluxDB to handle all the metrics. It was around 30 gigabytes. We knew that for customer visible dashboards, we need about 5% of all metrics. And some additional dashboards for support team may also need another 5%. All other metrics were added some time ago, and seems like nobody was looking at them. So we decided that we have the power to say that we will drop them and not push to internal monitoring. Any team which would need to add some new metric for internal monitoring would need to go through our review to ensure that nobody sends high cardinality data to internal monitoring. Also, we changed push interval to a minimum which was required by product managers. ECS UI showed data points for every 5 minutes, so we changed push interval for all metrics to be 5 minutes, on Telegraph as well as on services which produce metrics. Effect was amazing. InfluxDB memory consumption dropped to around 2 gigabytes. That's all we needed. But when we set up longevity testing on our cluster and it was running for a few months, we discovered that after a few months, InfluxDB started to consume much more memory than we expected. We knew that keeping long history will cost some resources, but the amount of resources used by InfluxDB was too high. After investigation, we found that the problem was in the InfluxDB index. Remember that every database in InfluxDB has a retention policy, and every retention policy has a shard duration, which defines how many shards will be there in your database. Like if you have 2 months retention policy and set shard duration to say 1 day, you will end up with 60 shards. But every shard has its own index, and index is the most resource consumptive part inside InfluxDB. If you have 60 shards in your database, you will have 60 indexes in them, and 60 indexes will consume much more resources compared to say 10 shards with the same retention policy. So remember a rule of thumb. Try not to use more than 10 shards per retention policy. It is fine to use 1 shard per small retention. For larger retention policies, keep in mind that InfluxDB supports retention by removing shards which contain only data points which are older than retention policies. So if you have shard duration of 10 days, InfluxDB sometimes will have in database points for extra 10 days older than the retention policy, until InfluxDB will be able to remove all this shard. Never use shard duration which will produce you more than 10 shards for your retention policy. But be aware that you will pay by memory for it. Finally, we are done optimizing Telegraph and InfluxDB. Provided FluxD and Grafana just enough memory for functioning normally, and may relax knowing that our monitoring stack will never goes out of memory on customer side. But we had a few more use cases which required memory optimization. Remember that ECS is operated by customers in big data centers. Guess what? Sometimes customers use external monitoring and need all the metrics from a system to go into this external monitoring. Our first attempt to provide solution for this use case was simple. External monitoring just periodically polls FluxD to get needed data. Sounds simple and right. But we quickly found an issue in this approach. External monitoring needs a lot of resources, so it runs a lot of queries. It makes FluxD busy and occupying memory more than we wanted. Also, it even loaded more InfluxDB instances, which had all the time retrieve lots of raw data. Also, we knew that external monitoring has much more free resources than we have on internal monitoring, and we may build much more complex dashboards with much more details there. On internal monitoring, we do not push all possible metrics from the services. We push only critical ones, which are required for customer and for troubleshooting. So, if external monitoring pulls metrics from FluxD, it will have access only to the metrics available in internal monitoring, but we wanted more. Solution we found is to push all the metrics from Telegraph instances, not only to internal FluxDB, but also to external monitoring instance. We did not apply any filtering logic for this external output, and this allowed to push all available metrics. As metrics are being pushed at this time of creation, it does not add much resources to Telegraph, just the size of a single memory buffer. That's not much. And now, customer gets all the data needed from the system on external monitoring, and we even were able to provide much more details on the system health and capacity breakdown details on the external monitoring system using extra continuous queries. This approach allowed us to keep control on low resource consumption of monitoring components for the use case of integrating external monitoring into the system. In this section, I showed you how we were able to control memory resources in InfluxDB monitoring stack by using techniques like limiting Telegraph buffer, avoiding using exec input plugin in Telegraph, offloading compute out of InfluxDB, filtering out all non-needed metrics, sending metrics with as low frequency as you can to satisfy your requirements, and pushing metrics to external monitoring directly from Telegraph. Now I will provide you a brief overview of the steps we had to do to actually switch our monitoring stack. First, when we started to work on changing monitoring stack for ECS, there was already a working monitoring framework. All services were pushing metrics to statistics framework. UI used a special dashboard service which prepared data from statistics framework. And we also had an alerting framework with different alert rules defined. Some of them use statistics framework to alert on metrics, but again, all the queries were written as pure Java code. When we started to introduce new monitoring framework, we knew that we will not be able to switch everything at one shot in a single release. So we decided to go with a strangler application pattern and build new monitoring framework which would work in parallel with old monitoring framework, as we would need a few releases to switch monitoring stack and cannot degrade any of the functionality which was already working from monitoring and alerting perspective. We added a simple logic in our low-level library in the services which was responsible to push metrics to statistics framework, and now it was able to send metrics to both stacks. In addition to statistics framework and send all metrics to local Telegraph instance, once we had this feeding of both monitoring stacks with metrics, we were able to non-disruptively add some new system-level dashboards in Grafana and release the next version of ECS. Now customer support had much better dashboards to faster find issues looking at system metrics like CPU, memory, swap consumption per each service. Grafana was deployed on demand by customer support. For next release, we were able to integrate ECS UI and alerting framework to be able to get some metrics from new monitoring framework, which allowed to add some new panels inside UI and add new alerts in alerting framework using Flux queries. In this stage, we embedded Grafana as iframe into ECS UI to avoid a need for separate authorization for Grafana. And we also added some new customer visible dashboards in Grafana and released a next version of ECS. After that, it was possible to move all monitoring related functionality to use FluxD queries and retire old statistics framework. By following this strategy, we were able to continue making releases of ECS while changing monitoring stack under the covers, improving monitorability of our product and making service teams more autonomous when they were able to add new alerts or build new dashboards just using Flux queries. Let's get a quick look on what dashboards we got as a result of changing the monitoring stack. As I said, there are lots of new dashboards added and I will not be able to show all of them. Just a quick overview of few. Performance dashboards. We were able to add different performance characteristics, including split by method type, protocol. Also, we were able to build detailed dashboard on system latency to show not averages of latency, but P90, P50 percentiles. As you know, this makes a huge difference in understanding a real latency of a system. We also built system metrics dashboards. They show node level as well as per process system statistics like memory, CPU, swap used. These dashboards helped a lot when investigating different issues on customer side and are the first ones which are being looked at by customer support team when root causing an issue. We also built a top-end buckets dashboard. It shows the customer which are the biggest buckets on the system in size and in object count. It would take me another hour to go over all the dashboards which we were able to build using new monitoring framework. There are lots of them. Now we reach the end of my story and I want to make some final notes.
In summary, we proved to ourselves that InfluxDB is a great time series database. It is extensible enough to add high availability features on top of open source version. It may fit into low memory resources if you carefully work with it. It may be used as internal monitoring solution for on-premise deployments. So, good luck using it in your product. If you have any questions or feedback, please feel free to connect to me on LinkedIn or send me a mail.